All right, my friends, section 11.5, part 3 is about finding exact area. So what I'm going to do is give you a couple of examples to help kind of build you into the concept. This example, I think this is example 5. Is it example 5? Example 6. Okay. Is going to be a little bit of a hybrid where it's kind of the approximation type stuff still, but I'm trying to bridge you into the new piece here. So the directions are: use a right endpoint, Riemann sum, to write an expression that approximates the area. Okay, so here's a picture for you. So let's say that you are given some function f, and we're going to keep f generic. In the last couple examples, I gave you a function rule for f, and on this problem, we're going to purposely keep it generic. And this time we'll have the interval be from 2 to 6. And so the shaded region that we're going to approximate the area for is right here. And then I'm actually going to edit the directions just a little bit. So it says use a right endpoint Riemann sum. Riemann sum, by the way, is just rectangular, using rectangles, to write an expression that approximates the area. And let's say we're going to use, so this time using 8 rectangles of equal width. And WIDTH. Okay, I am going to kind of lead you through some thinking that will help you when we start making this a little bit more interesting as we go. So the first thing I'd like for you guys to tell me is, how wide is this interval at the bottom? And so I hope that you could either just look at it, or you could do 6, take away 2, and find out that you've got 4 units here. So you have a total of 4 units, and then you're supposed to fit 8 rectangles, and they're all supposed to have equal width. So how wide would each one be? So we could say that the width of each rectangle, and if you're thinking it's 1/2, then you're dead right. And I hope it makes sense if I was to say that you could get it by doing 6 take away 2 divided by the number of rectangles, 6 being, you know, the greater of the 2 x values on your interval, 2 being the lesser, and then dividing by the number of rectangles. Whoops, the number of rectangles is not 4, sorry guys, it's 8. And you'd get that common width of 1/2. Okay. So now let's talk about approximating the area. So there's 4, and now 4, splitting each of those in half. Okay, so if I was to draw a picture, we're using a right endpoint sum. So here's one of my rectangles. So I would say the area of the shaded region is, please use approximately equal to marks, not exactly. And so let's figure out how to calculate that right there. So the base is 1/2, we already figured that out. And then what would you multiply that by to get the area? Well, you'd multiply it by the height. So what x value is that? Well, you started at 2, you went to the right half a unit, so you're at 2.5, also known as 5/2. And so you would, how would you get the height? I never told you what the function rule is, so the expression you would say is just whatever the function rule is, you'd plug in 5/2 into it. Or you could say 2.5 there, nobody cares. Rectangle number 2, you'd multiply 1/2 by what expression here to get the area? So the height, this x value would be 3, and so you would plug 3 into the function rule, so you just do f of 3. Rectangle number 3, whoops, you do f of 3.5. Next rectangle, f of 4, f of 4.5, f of 5, f of 5.5, and f of 6. There we go. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. There we go. And that would represent each of these little, the area of each of these little rectangles. And it would be an approximation of the area that's shaded using a right Riemann sum. Okay, and it just said an expression here, so there you go. That's your answer. Okay. Another way to say this same thing to avoid all the repetition would be to use sigma notation. So the 1/2, that width, could be factored out. And then how on earth could we express this mess by using sigma notation? Well, you could have said the sum as I goes from 1 to 8 of f of 2 plus 1/2 I. So let's think this through really quick if that made no sense just now. If I was a 1, then you'd have 2 plus 1/2 here. So that would be this expression right here, 2.5. If I was 2, then you have 2 plus 2/2. So that would be 3, so f of 3. And then the 1/2 got factored out because, it's a common width anyway. So hopefully this little sigma expression kind of makes sense. And if not, then we'll work on that as we keep going. So either of these last two answers would have been perfectly great. Either this answer or this big messy one up here. Okay. Let's move on to example 7. Directions are to use a right endpoint. You're going to notice that I stick with right endpoint stuff from here on out. You'll see why by the time we're done. To write an expression for each height. Okay, so these examples are kind of a little more exercises just to kind of get you used to where we're going with this. Pretend that looks like a nice, beautiful, perfect x-axis right there. Time to use your imagination. Okay, so again, we're going to stay generic with the function rule. Last time I told you what the endpoints were in numeric version, but this time I'm going to just say we're going from A to B. And we are going to approximate this shaded region here, the region bounded between the graph of f and the x-axis on the interval from a to b. So, so let's see. Let's first of all, from here on out, when we use the letter n in this context, the n is going to represent the number of rectangles. So for this example, whenever you're thinking about the number of rectangles, just use the letter n, and that way it would work no matter how many rectangles you're using. So, and we're going to use a right endpoint sum. And so let's think about what would the height of the first rectangle be? So it's a right sum, and you've got n rectangles, and actually, you know what? Sorry, guys. Let me wait to ask that question. Before we do, let's talk about if there's n rectangles, what would you guys say the width of each rectangle is? It's pretty important that we stop and think about that. Width of each rectangle. Okay, so how much width do you have down here from A to B? How far, what's this distance? So it would be B, take off A. So this whole distance down here, from here to here, would be B, take away A. And then you're supposed to cram in n rectangles. We're not saying what number n is, but you're supposed to cram in n rectangles. So how wide would each one be at the bottom if you're fitting in n and they're all supposed to be the same width at the bottom? Well, you take this width you have available, b minus a, and you just divide that by the number of rectangles. And so this expression, I hope it makes sense, would represent the width of each rectangle. Now let's talk about what would the height, H-E-I-G-H-T, there we go, of the first rectangle be. And let me show you on the picture what I mean by the first rectangle. So the height of the first rectangle, so let's say you, this width right here, you go over a little bit from A. So I'm going to break this into a couple of questions. First, if you just bumped over this width amount right here, what is that x coordinate right there? You were at A and you moved to the right this distance. So what's the x coordinate right there? Well, it would be A plus whatever this equals. And then we're using a right endpoint sum, so what would the height of this rectangle be? Well, you'd take this x value and you'd plug it into the function, and that would give you the height. So the height would be f of a plus b minus a over n. And then because it doesn't hurt anything, I'm going to say times 1. You'll see why in a second if that doesn't make sense yet. Okay, now let's talk about what would the height of the second rectangle be. So that would be, okay, so like let's say this is your second rectangle. Okay, so break this into a series of questions. So first of all, what x value is that? Well, you started at A and you would have bumped over 2 widths. So that would be x equals A plus b minus a over n times 2, because you started at A and you went down the x-axis 2 widths, and each width is one of these. So what would the height be then of that rectangle? Well, you'd take this big, scary looking x-coordinate and you would plug it into the function rule, and that would give you the height. So f of A plus b minus a over n times 2 would be the height of the second rectangle. And then I think we'll kind of keep up with this just a little bit more, and then we'll kind of show you where we're going with this. So what would the height of the third rectangle be? So third rectangle, what would the height be? Well, that x-coordinate would be, you would have bumped over 3 widths from the starting number, so it would be a plus 3b minus a over n's. And then you plug it into the function rule. And I'm hoping that if you look at all these expressions, you'll notice that there's a lot of repetition. You'll have f of a plus b minus a over n, and the only thing that is changing is the number of those widths that you bumped over. So if I was to ask you, hey, do you notice a pattern? And the next thing I'm going to ask you really to do is kind of to write a pattern. So if I was to say, what's the height of the ith rectangle? As in, no matter what number you're on, what's the pattern, you know? So I hope that you could see the number of rectangle you were on matched this number right here. First rectangle, you bumped over 1 width. Second rectangle, you bumped over 2 widths. Third rectangle, you bumped over 3 widths. So to get to any rectangle, you would do, for the height, you would do f of a plus b minus a over n times I. Okay. So now, what if I asked you, well, what would you say the sum of all the heights is? So, and when I say sum of all the heights, I mean you'd be adding up, the height of the first one, the height of the second one, the height of the third, all the way up to the height of the nth one, since we said there was n total. Well, you could really use sigma notation. You could say, oh, well, it would be the sum as I'm going to let I be my index, as I starts with the first rectangle, goes all the way to the nth, and then the rule that you could use would be f of a plus b minus a over n times I. So, and if this doesn't make sense yet, then play with it. See what happens if you were to expand it out. If you were to plug 1 in for I, notice that it would say this expression. If you were to plug 2 in for I, it would say this one. If you were to plug 3 in for I, it would say this one. If you were to plug n in for I, it would actually say f of b, which makes sense because it was a right sum, and your very last rectangle should have a height of f of b. Now, where are we going with this? We're really going to go into finding an expression for the sum of all the areas. And let's think that through for just a second. I'm going to get my orange pen out. If instead of height right here, and you don't have to cross it out in your notes if you don't want to, but I hope it makes sense. If I took the word height there and put area in, you would just take the height and you'd multiply it by the base, and the base of each one would be b minus a over n. So you'd have a little, that guy there. And then if I took height out here, replaced it with the word area, then you'd have in front of this height, you'd have b minus a over n, base times height, base times height, base times height. So then, and again here, if I took the word height out and put area in, then you just have to multiply by the base expression, base times height. So what could I write for the sum of all the areas? Well, since this is a common factor, you could factor it out front. Since after all, since the sum as I goes from 1 to n, the index is I, so everything else is a constant. And then you could just have the sum of all the heights in here. So here you have the sum of all the heights, and then here you'd be distributing the width into each one if this was expanded out. So now let's think about getting more toward the concept of the day, which is finding exact area. So I hope it makes sense. You know, in the last, I'm going to go back to example 6 and refer to this really quick. I hope it makes sense that the more rectangles that you can cram in to a subinterval, the less error you have. So like this little error chunk here, these little pieces get smaller. So like in the last example, we had 8 rectangles, which was tedious enough. But if you needed a little less area, maybe you could cram in, we're so not doing this by hand, but maybe you could cram in 16 rectangles. And then you would reduce the amount of error if you did that. So theoretically, how many rectangles would you need to cram in to a interval to get no area at all? And so I hope it makes sense that you'd need to cram in infinitely many, infinitely thin rectangles in order to get exact area. So this is actually going to be easier than you'd think. So to get exact area, you're just going to let the number of rectangles approach infinity. And of all this gobbledygook, which letter represented the number of rectangles? And it was n. N represents the number of rectangles. So to find exact area, it's really just this expression with the limit as n approaches infinity written in front. There we go. Okay, now it's up to you how you want to go about this. The way that I'm teaching this, you would not have to memorize this formula. You could think it through conceptually each time. And then some people kind of decide that they want to lean on memorization a little more. I will tell you that understanding conceptually is going to last you a lot longer and be more empowering. In Calc BC, we'll have some moments where we need to do things like this in 3 dimensions. And so understanding it conceptually is going to be more important than memorizing a formula that will not work when you go outside 2 dimensions, which this one is only for 2. So, so consider that. Okay, so with that said, let's look at an example where you will find exact areas. So example 8. Let's do this in 2 parts, I think. Part A, write an expression for the exact area of the shaded region. And let's bring back the one that we had worked on previously. So let's do f of x equals x squared. And then let's just do the interval from 0 to 2. So a couple comments, if you were going to lean on the formula, your A value here would be 0, your B value would be 2, and then your number of rectangles is n, and you'd be letting the number of rectangles go to infinity. But if you are going to just try to think this through conceptually, which I do recommend, it's a lot more empowering, then you'd be thinking of, okay, well, n is always the number of rectangles. And if that's true, then what would the width of each rectangle be? So it would be the 2 units that you have here, which you could think of it as 2 minus 0, divided by the number of rectangles, which is n. Okay. Now you could think about, you could kind of teach yourself a pattern, and I'm going to show on paper what would happen in your head when you get used to this. Right now you'd probably write it on paper. So you could think about what would, say, the area of the first rectangle be. And we're supposed to fit in infinitely many rectangles, but you can't draw rectangles that are that skinny. They just look like little sticks. So I'm going to go ahead and just draw it like way wider, of course, than it would really be. But let's say this is my first rectangle. So you start at 0 and you would have bumped over one of these widths. So this would be x equals 0 plus 2 over n. And so the area of that first rectangle, we always use a right sum for this because it's easier to see the pattern. So the area of the first rectangle would be your base times your height. And I'm just going to say times 1 because it doesn't hurt anything and it helps to show the pattern. And then what would your area of your second rectangle be? So let's say your second rectangle is here. So your x value would be, you started at 0 and you would have bumped over 2 of these widths. So you could say 4 over n, but it's probably a little better to say 2 over n's for pattern purposes. So what's the base of the rectangle? It's just 2 over n, and then the height would be f of 2 over n times 2. And by the time you've done this, you can start seeing a pattern emerging as to what's staying the same and what's changing and how that relates to the rectangle you're on. So if you were to do this conceptually each time, then it would probably be a little bit better for your brain as opposed to just plugging things into a formula. But the point is that the area of the shaded region would be exactly the limit as the number of rectangles approaches infinity of the sum, I'm gonna show this in 2 steps. The sum as I goes from 1 to n of, and then you'd just be showing the pattern here. So of 2 over n times f of 2 over n. And notice first rectangle, you have 1 2 over n. Second rectangle, you have 2 of them. So for any ith rectangle, you just bump over I of those 2 over n's, plug that into the function to get the height, and then multiply by the base. This is a perfectly fine answer for this particular problem. However, typically you'll see the 2 over n factored out right there. Because as we've mentioned in previous videos, it's a constant as far as sigma is concerned, but not as far as the limit's concerned. Something along those lines, okay? Now, this is an okay answer, but because f of x was just defined for this problem as x squared, then we can actually keep going. So I'm gonna make a note between this step and the next one, and it is, since in this problem f of x was defined as x squared, f of, and this right here I'm gonna write as 2i over n, would be, just plug it into the function rule. In this case, it was x squared, so f of 2i over n would be 2i over n squared. Simplify that. fight the urge to replace I squared with -1. Here we do not use I to mean the imaginary number, so don't do that. And so what that means is that this expression right here could be replaced with 4i squared over n squared. So the best answer to this problem where I asked you to write an expression for the exact area would be the area is the limit as the number of rectangles approaches infinity of the width of each rectangle, 2 over n, times the sum as I goes from 1 to n of 4i squared over n squared. And I'll probably box that up. There we go. And I hope this is making sense. This is usually the type of lesson where I get a lot of questions as we go. So it's kind of weird to be teaching it without anybody here to ask questions. Okay. Part B, let's say I ask you, now that you have your expression, I ask you to evaluate it. Well, that's where hopefully you watched the first video for this lesson, because you're going to need to be using those techniques. So your area would be, first thing I personally would do would be to factor out the 4 and the n squared out of sigma. How come? Because as far as the sum is concerned, I is the variable. I goes from 1 to 2 to 3 and so on. So other factors are considered constant multiples as far as sigma is concerned. So I would have the limit as n approaches infinity of that 2 over n that's already there, and then I'd also factor out the 4 over n squared. I'd be left with the sum as I goes from 1 to n of just I squared. From there, I would have the green light to sub in a formula for this sum in terms of the upper bound n. So I'd have the limit as n approaches infinity of, I'm going to go ahead and merge this together as 8 over n cubed, and it would be multiplied by n times n plus 1 times 2n plus 1 over 6. Okay, now from here, let's think about, well, what would the limit as n goes to infinity of this expression be? And you could use the relationship between infinite limits and horizontal asymptotes, or end behavior. So what's the degree of the numerator? It is 3. What's the degree of the denominator? It is 3. Since the degree of the numerator and the denominator is the same, you will have a horizontal asymptote, and it will be of the form, the leading coefficient of the numerator, which would be 8 times 1 times 1 times 2, or 16, over the leading coefficient of the denominator, which would be 6. Simplify your fraction, you get 8/3, which might make a little more sense if we were to say 2 2/3 units squared. There we go. Exact area of that region. And in a previous video, I had told people to see if they could guess what the answer was. And if your guess was anywhere near 2 2/3, then that's pretty great. All right, my friends, we're going to do one more example just to make sure that you've got it. It'll have 2 parts, and then we'll be done with chapter 11. All right. So example 9. Directions are for you to find the exact area of each shaded region using the limit process. The limit process just being what we've been doing, since it has that limit as n goes to infinity on it. Okay, part A. This time we're going to use f of x equaling x cubed plus 1. I'm going to use a scale up here of maybe 7s. Okay, so x cubed plus 1, plug 0 in, you get 1 out. Plug 1 in, you'd get 2 out. Plug 2 in, you would get, what, 9 out? And plug 3 in, and you would get 28 out. Okay, so basically the shaded region in words could be described as the region bounded by the graph of f of x. Let me write this down. F of x equaling x cubed plus 1 and the x-axis on an interval from 0 to 3. Super good time to pause the video and see if you can do it on your own, and then check with me where you need to. If I was doing this, I would set it up so area would be the limit as n approaches infinity of the width of each one would be 3 units divided by the number of rectangles. And then in here, I need to have the sum of all the heights. So if you start with the first rectangle and go to the nth, you would, I think for starters, I'll just do f of, and then I'll kind of specialize it for this function rule in a little bit. So we'll do f of, you're starting at 0, and then each rectangle you would bump over your width, which is 3 over n. Like so. Now, since f of x, I'll just kind of work that out here. Since this time f of x is equal to x cubed plus 1, f of 3i over n would be 3i over n cubed plus 1, also known as 27i cubed over n cubed plus 1. So that would give us an area expression of the limit as n approaches infinity of 3 over n times the sum as I goes from 1 to n, and we're just going to replace f of 3i over n with this expression. Using grouping symbols to show that this whole expression is something you should apply and use as the rule for the sum. Okay. Now for figuring out how to write this in terms of n. Notice you're going to bring down your notation, my friends. Write the limit as n goes to infinity still. Bring down 3 over n. And then let's distribute the sum over addition next. So I'm going to use some grouping symbols so that this stuff gets applied in. All right, and then I'm going to use the constant multiple rule on this sum right there. So as far as the sum is concerned, I is the variable. So 27 over n cubed can be factored in front. And then you could recopy this as is, or you could just take care of it right now. I'm going to go ahead and just take care of it right now. So that's just n times 1, or n. Try to remember, though, that this is not part of the rule inside the sigma notation. If you have a sum and you do want it all be part of the rule, you should use grouping symbols to indicate so. All right, now working on this piece right here. We're going to write the limit as n goes to infinity of 3 over n times 27 over n cubed times n squared times n plus 1 squared over 4, and then plus n. Okay. For me, let's see, I think I would recommend kind of, if you're going with a bare minimum approach, I would go ahead and distribute the 3 over n in like so. And I don't think I'm gonna work super hard at it. So let's see, 3 over n times this first expression, I'm just gonna write it as 81. So 3 times 27 is 81. And then on the bottom, I'd have 4n to the 4th. Now, can some n's cancel? And could this be simpler? Sure, but I claim it kind of doesn't matter because of what we're gonna get out of it anyway. 3 over n times n is just 3. Next, I hope it's okay if I don't write it, but recall that limits do distribute over addition. So we could figure out what the limit as n goes to infinity is on this expression, figure out what the limit as n goes to infinity of this one, and then just add them together. So with that said, let's look at this top part. Notice the numerator is degree 4. The denominator is also degree 4. So you would have a horizontal asymptote. It would be at your leading coefficient in the numerator divided by your leading coefficient in the denominator. And since limit as n goes to infinity is asking about n behavior, you would just say this expression basically gets infinitely close to 81 over 4 as n gets infinitely large in magnitude. Then limit as n goes to infinity of 3 is just 3. All right, so 81 over 4, what is that? 20 and 1/4, and then you're adding 3. So 23 and 1/4 square units. And if you pause the video and got that on your own, then that's incredible. But if you watch the video and this makes sense, that's also super incredible. All right, my friends, notice I'm saying the area is exactly equal to 23 and 1/4 square units because we are no longer approximating. We have just found out if you cram in, and so if infinitely many, infinitely thin little rectangles into this region, we just added up the area of those infinitely many, infinitely thin rectangles, which would all look like a bunch of little sticks. And that's what we got. All right, exact area. Okay, one more. I'll give you a nice little challenging one to finish it off. Okay, so we're going to go from -1 to 2. And we're going to use f of x equals x squared plus 3. Okay, 2, 4, 6, 8. Okay, that's probably fine. Okay, so plug 0 in, get 3 out, 1 in, you get 4 out, -1, you get 4 out, and plug 2 in, you get 7 out. Okay, that looked horrible, but that's all right. Hopefully, so just to make sure we're clear, this function rule is f of x equaling x squared plus 3 this time. Okay, so we are finding the exact area of the region bounded by the graph of f of x equaling x squared plus 3 and the x-axis on the interval from -1 to 2. Okay, good time to pause the video and see if you can get it. If you get it right, the answer should be 12 square units. So I'll go through it and show you how I would show it. And then make sure if you do get 12 that when you watch the video, you're checking to make sure your notation is intact the whole time. I'll be looking for it when I grade your test. Okay, so the area will be the limit as n approaches infinity, number of rectangles approaches infinity. You've got 3 units. The the width of each rectangle would be 3 divided by the number of rectangles. And then you would have, you'd multiply that by the sum of all the heights. So you'd take your function rule and you would plug in. Notice that the interval starts at -1. So your first rectangle that you would draw, and I know this is not an infinitely thin rectangle, but use your imagination. Your first rectangle that you would draw, you would have bumped over one of your widths, which is 3 over n, from -1. So the x-coordinate would be -1 plus 3 over n. Your second rectangle, your x-coordinate there would be -1 plus 2 3 over n's. So the x value you should plug into the function rule to get the height would be -1 plus your width times whatever number of the rectangle you're on. Okay, now since in this case f of x is defined as x squared plus 3, f of -1 plus, I'm going to call this 3i over n, would be -1 plus 3i over n squared plus 3. All right, simplify this mess. What do we get? 1 minus 6i over n, I think, plus 9i squared over n squared, and then don't forget about that plus 3 right there. It's a common mistake. All right, and then I'm going to write this in descending powers, so I'm going to write it as 9i squared over n squared minus 6i over n, and then the 1 and the 3 combine to make 4. Okay, so taking that and running with it, we would have that the area would be the limit as n approaches infinity of 3 over n times the sum as I goes from 1 to n. Oops. And then we're going to replace f of -1 plus 3 over n times I with this expression right here. Okay, so now we've got the limit as n goes to infinity of 3 over n. We're going to distribute sigma over subtraction and addition. Don't forget a grouping symbol, so this gets multiplied by everything. Actually, you know what? Let's skip a step. All right. Right after we distribute sigma over addition and subtraction, we're going to factor out the constants. So I'm going to show what we'd have after that. Okay, now from here, bring everything down. Be a pack rat with your notation. Believe it or not, math gets more complex than this. As soon as you start trying to solve the world's real problems, math gets really messy, and you want to have a way to keep everything together so you don't lose big ideas. So replacing this sum right here with its rule in terms of the upper bound. Okay. Replacing this rule right here. And then replacing this sum right here. Like that. Whoops, like that. Okay. Now I think the only thing I'm going to bother with is distributing this in, maybe doing a little minimalist of cleaning up. You shouldn't have to do a lot. Okay, so multiplying 3 over n by kind of this piece here, we'd end up with, I'll just do 3 times 9 is 27. On the bottom, you'd have 6n cubed. 3 over n times the second piece, looks like you'd have 18 2n squared. 3 over n times 4n would be 12. Like so. Okay. Right? The n's cancel, you're left with 12. Okay, great. Okay, now let's look at n behavior. Limit as n goes to infinity. What would happen here? Degree of the top, 3. Degree of the bottom, still 3. Leading coefficient of the top would be 27 times 2. Leading coefficient of the bottom would be 6. So the limit as n goes to infinity of this first expression would be whatever 27 times 2 over 6 is. Limit as n goes to infinity of the second expression, remember limits do distribute over subtraction and addition, would be your leading, so degree 2, so leading coefficient of the top divided by leading coefficient of the bottom, which would be 18 over 2. And then limit as n goes to infinity of 12 would just be 12. Okay, so canceling things down, like maybe the 6 and the 27, 3 goes into both. And then the 2's could cancel out. So you're left with 9 minus 18 over 2 is 9 plus 12. That is a way to get your final answer that the exact area of that region would be 12 square units. All right, my friends, thanks for hanging in there with me. I hope this all makes sense. It's a lot of craziness, but that's conceptually how we find exact area of regions that are beyond what you would have learned in geometry. All right, take care, everybody.